Welcome to this new module, that is module number 4, and which is basically the HVDC system faults and protection. And today I will discuss the lecture 1, and in this we will see the various faults in HVDC system, including AC as well as the DC side, and then we will see what are the repercussions, what will be the problems during these fault conditions, and then at the end I will discuss about the protection scheme for the HVDC link. We know HVDC system, basically we are having, if we are talking about the two terminal HVDC link. So, we are having one rectifier, we are having one inverter, and both side is the AC system is there. So, the fault can be the rectifier and AC system, and also it can have, so the fault may be there, and another there is a possibility that fault in the converter itself, in the station itself. So, general here in the HVDC transmission system, if we are talking the two terminal system, here is a 3-phase system, and here we are having the DC supply, here the line, and this is your inverter, and we are having here 3-phase supply system. So, fault may be this side, fault may be this side, fault may be in this DC line or cable, whatever it is, and then it may be the possibility that there is some problem here in the converter or inverter station itself. So, if the fault occurs this side, no doubt it is a AC system, and the protection of AC system is very strong. We are having the protective relays, we are having circuit breakers, and then it will take care of that fault. But no doubt any protection system in AC system, it requires several cycles to, because your relay will sense the fault, then it will give the signal to your circuit breaker, and then circuit breaker will operate. It may require 2 to 5 cycles. During that period, this your converter station will experience a very excessive, either the voltage high or voltage low, depending on your fault. You know very well that the fault in the AC system can be a symmetrical fault, means that is nothing but is a 3-phase fault, or it can be asymmetrical fault, it may be line to line fault, it may be line to ground fault, it is a 2-line to ground fault, and so on and so forth. And depending on that fault, the voltages in the phases are varying. If it is a dead 3-phase fault, means the voltage will be 0, and then at that time here the DC voltage will be 0, and your current situation will be the different. Your the converter control will be acting accordingly during the fault, suppose it is happening here. No doubt this AC protection system will take care of the fault if it is happening this side, but during that fault duration, this your link controller will act, because the control action is very fast compared to the protection system here, and your system will be adversely affected. Now, here the voltage may rise also depending on the asymmetrical fault. If the fault in one line is there, if neutral is not connected properly, the voltage of other field may be go above, that is a voltage. Over voltage may experience by this converter, maybe under voltage, sag may be there, and of course, sometimes voltage may be 0. So, I am not going to discuss in detail, because we are not concerned about the AC protection system. Our concern here is HVDC faults and the protection. So, here we are talking inside this system, the DC, this converter, including this rectifier and your DC system. So, that is why here I have classified there is a 4 subgroup, I can say. This is the first one, this is your rectifier side fault, this is your inverter side AC fault, and then the fault corresponding to this DC system, and third is in the converter stations itself. So, it can be categorized in the 4 faults here. Major concern here in the converter station, because if there is some problem here in the valves, firing, misfiring, whatever happening here, that is directly related to that it will inject the harmonics in the DC side, as well as it will introduce various harmonics in the AC side as well. So, we have to see what are the various mal-operation of this converter station, is here rectifier including your inverter as well. If the fault occurs this side in the DC line, you can see here I have made a table. You can see this converter and internal faults are very rare, no doubt. I am talking about the faults inside. What will be the fault, we will discuss in this slide itself, in this lecture itself, but the current here can go very high, because the current is directly controlled by the voltage of this as well as this. If this voltage has gone down very less, current may exceed, or vice versa. So, you can see here the converter and internal faults are rare, no doubt, because we are having so many safety factors. For example, I told you here for making one, as normally I said here, this is your valve 1. This valve basically is consists of several thyristors, several GTOs. They are in series as well as a parallel combination to make it sustain the proper voltage and the proper current. And also we give some safety margin here. If required is 4 thyristors, we go for 5 or 6 thyristors. Even the one is punctured, still we can operate this whole valve successfully. So, here of course, the fault is very rare, but it is very severe, because your current can go up to 10 per unit. And now if it is going very high, what will happen? Some of the thyristors will be carrying this per unit current, and that may damage it. But what we do normally, these are having some for a small duration, because your control action will take care, because there is some problem here, current will increase, your controller here they will work very fast, and they will try to reduce. For that momentary periods, this thyristors can sustain even though for higher voltage. So, that is why protection is there. DC line fault, which is the frequent. Why? Because if it is a transmission line, it is on the towers and it is exposed to atmosphere. So, always there is some dust on the insulator, there may be some fogging, or there is some wets are there may be flashover if even the small voltage rises and there. So, it is a very common and maybe self clearing as well, and the current you can see it is going to be 2 to 3 times more if the fault something here occurs here. But what happens if the fault occurs in the DC line? Because one of the here converter is controlling current. Once current is going higher, this converter will work in such a fashion, it will try to reduce the current. But once it has sensed the current has gone very high, then we have to operate one converter here, that it can be maintain the voltage 0, or we can just go for opening of this line. If the fault here, let us suppose it is happening here. Now, there is a 2 type of fault here in the DC line itself. There is a possibility that fault between the 2 poles itself, that is just similar to line fault in AC system, which is very rare, because it is very spacious. It is very rare, no doubt, line to line fault, unless until really you are having some wire between the 2, you are connecting by some means. But from 1 to the ground, it is very common, because you know what is happening, it is your tower and it is just your here, this is the insulator and your conductor is passing here. You know there is some problem, so there is a spark over and this is a grounded. So, this is a pole to ground fault is very common, because there will be some flashover here due to some dust, some impurity, some high voltage here, and then it will be grounded. So, it is a pole to ground. Another here, as this is insulator, another pole is here. So, the connection between these 2 is very rare, no doubt this may be possibility here ground, both are short circuited, but it is very rare. So, when current is going to increase, then controller will act. It will try to reduce the voltage, or it will try to do in such a fashion that we can just maintain the current and then we can reduce, so that we can inspect for the faulty line and we can just clear the fault in this. So, it is again, as I said, it is a force retardation of the firing. What we do, we do angle change here simply, so that we can maintain the current and finally we can make it 0, so that the fault can be cleared and we can be inspected. Another fault is the commutation failure, which is you can say very frequent, especially, and this commutation failure always occurs in an inverter. We will discuss more detail about the commutation failure, because commutation as word is a current, that is a incoming valve is unable to accommodate, take care of complete current, means from valve, let us suppose the commutation is occurring between 1 and 3 here. So, the current which was earlier taking ID current here, it must be taken by the valve 3, but due to some problem, the problem normally the voltage which is here is going to increase, here the voltage is going to decrease, because certain very small duration where the voltage will be positive across this, and it is a reversing. If it is not taken completely here, there is a failure, means it will not take the current completely, and again the current will shift from here. Means here for let us suppose this is a current I1, this is your I can say ID, it is flowing here. Now, this is ideally this I3, this is your going to be this like this here. This is the during the commutation period, the current of I1 should decrease to 0 and I3 should take complete ID. But what happens here, normally this current is coming here and again this is going here and this I3 here becomes here. Means it is started taking current, but finally due to the change of voltage here is going to be in the negative side. Possibility that it is again going back in the 0 state, means current is not taken completely and the current is shifting from here to here again, and then it is I1 is taking current. So, what happens now, you can see the sequence is failed. Normally what we say, here your 1 and 2 are conducting, then here 2 and 3 should be there, but 1 is not coming, again 1 and 2 is conducting. So, we will see what is the consequence of this in later stage. So, this is called commutation failure, because current is not commuted from valve 1 to another valve in that upper limb. If the commutation failure is a single means in one cycle, if it is happening once, then it is self clearing, because we will see no doubt 1 and 3 is connecting here. Later on, now the turn of 4 will come and we will find this, it is automatically cleared. But there is a possibility in between here there is another failure between, let us suppose here the 4 is fired or there is a 5th and 3 1 and 3 is not successful, then it is called double commutation failure in the same cycle. Commutation failure in one cycle, it is occurring once, it is a single commutation. If there is a commutation failure in one cycle twice, it is not in the same valve, it will be here 1 3 failure, there may be your 2 4 failure and so on and so forth. So, in one cycle if it is more than 1, it is called multiple commutation failure. That is very severe, and in that case the controller should take care and the voltage will go down in that case, and finally, we have to apply the video call controller and shift, and then we have to clear again back. So, this is basically the converter station fault here, which I am discussing in this portion only. Now, my concern here in this lecture that we have to consider basically about this problem here, either rectifier end or inverter end, and then what are the various possibilities of the failure in this converter station. So, according to the origin of malfunction or maloperation, the converter fault can be divided into 3 categories. One is your here the fault due to the malfunction of valve and controller here. Then we are having the commutation failure, which is completely for the inverter end, and then we are having the short circuit within the converter station itself, because there is a possibility here there is a positive polarity and there is a short circuit. So, inside the station, not we are talking here the DC line short circuit. I discuss all 4 separately. I discuss about this fault, I discuss about this fault, I discuss about this line fault, and then I am discussing only in this dedicated to in this converter station. Here in this itself we are having the 3 categories. One is basically due to this malfunction of valves. Malfunction means you are giving pulse, but it is not conducting, even the positive voltage is there, or it is conducting, again it is off due to some reason. So, this is basically malfunctions, we will discuss in detail all these things. Then another is the commutation failure, which is only occurring in the inverter end, and it is very common, very frequent, and here it is also known as the breakthrough, that is a failure to the complete commutation before the commutation EMF reverses. Then another is the short circuit within the converter station itself here. We are not talking short circuit here. Here short circuit there may be there is a shortage of various firing schemes or valves and so on and so forth. In this here the malfunction or maloperation of the valves, here it is categorized in 4. One is called arc back. Sometimes it is called the backfire, and this is basically it was only occurring in the Mercury Arc Valves, and it is in the modern thyristors and GTOs it is not the common. At that time you can say it is conduction in basically the when the voltage across this valve is when it is negative. Normally what happens in the thyristor, if the voltage across the valve is negative, if you are giving the gate pulse, it will not convert, it will not conduct any case. But it was a possibility that due to the negative some gate pulse is there, even though in the negative polarity the mercury arc valves were able to conduct it. So, it was only at that time it was the old stages. Then arc through here, that is a fire through or shot through, it is basically occurring when it is the voltage across this is the positive. When the voltage across the valve is positive, due to the rate change of the surges of the voltage across this or due to change of current in the passing through the valves, there is a possibility, because the dV by dt is maybe the concern, maybe di by dt will be the concern. In that case, here the arc through is happening. I will go detail each by each. Another is quenching. Quenching or arc quenching or arc shopping, what happens? It is conducting, but due to certain problem it is suddenly off. Means thyristor is conducting, the valve is conducting, but it is suddenly off due to the certain, that is called shopping, arc quenching. It was also very common, especially here the Mercury arc valve, because the arc concept is coming from there. Another is the misfire, and misfire as its name itself, it is the mist, means it is the sequence, voltage across this is positive, you are giving the gate pulse, but still it is not conducting. So, it should conduct, but it is not conducting, and it is known as a misfire. Now, you can see the possibility of all these four is very much can be recognized here by looking the valve voltages. You can say this is the valve voltage across rectifier operation, because the most of the time in the rectifier operation the voltage across the valves are either 0 or it is a highly negative, and the very small portion, you can see very small portion, it is a positive. It is a reverse here. So, that is why here the third is called the conduction period, when the voltage across valve is 0. When in inverse voltage period, it is called 1 period here, which is a longer period in the rectifier. However, it is a very small period here, the negative voltage in the inverter. And your blocking period is basically 2, blocking period here the voltage is the positive and we are trying to block, here you can see it is the most of the time. So, based on that you can see when it is going to occur in inverters, most probability is there, because if it is a arc back, so you can see in the negative period, if it is happening here, it is the most of the time it is a possibility here, because this is a longer period. So, we will discuss one by one all these arc back and backfire etc. So, let us see the arc back. So, this small operation which is the conduction in the inverse voltage period of the valve, inverse voltage means the voltage is negative, and occurs mainly in the rectifier, because this inverse voltage period in the rectifier is much larger than the inverter operation as we saw. So, this arc back occurs in the rectifier station, and as I said it was very much it was happening when it was the Mercury arc valves, because in the thyristors if the voltage is negative, even though your gate pulse is there, the chance of getting its conduction is very rare, almost nil, because this is a property of a thyristor, means it will only conduct if the voltage across this is the positive and the gate pulse is available. So, here that is why it is telling it was happening in the Mercury arc valve, but in the modern thyristors and you can say GTOs it is not so common. But this was also just I want to mention, because it was happening only in the Mercury arc valves and especially in the rectifier operation. So, it is most common and severe malfunction in the Mercury valve rectifier and the random in nature, because you do not know when it will be conducting in the negative side or not. So, it is random in nature. So, on average it is 1 or 2 arc back per valve per month, especially Mercury arc valve in the early ACE or HVDC links, they were using the Mercury arc valves, in that it was even the 1 or 2 per month it was happening. And the modern thyristors, that is why here do not suffer from the arc back. The factor increases the arc back, again I can say it is here the high peak inverse voltage. If the voltage across the valve is very high, then this may be, even though it can conduct due to the high voltage. The high voltage jumps, because you can say especially of the jump at the arc extension, here if you will see the jumps here, if the arc extension at this point, if you see here, this very high jump is there, because it was conducting here and then it is arc extension means is off. So, here there is very huge voltage here arising, and there is a possibility at this time voltage is going to very high negative, and then it may conduct in this period. So, especially jump at the arc extension, and another is high rate change of current at the end of the conduction. When the conduction is ending, then again the current may switch from again, although conduct here due to the U period, it is there is a rate of rise, but if this period is very small, then this will be suddenly it is going. So, it depending on U. If U is larger, then possibility is reduced slightly, but if U is here less, this rate of rise is very high, and there may be due to this again this arc back may happen. Another is your overcurrent. Again, if current value is very high, even the U is same, and this is high value, then again the rate is increasing and the possibility was there. Another, it was due to the impurity of anode and grid. You know the Mercury arc valves here, this is your cathode, this is your anode, and there was here a grid. If you remember the Mercury arc valves, in this here, if there is some impurity here, then that may cause the conduction, because this works on the ionization of the gas which is inside this valve. And another, the high rate of not size, high rate of rise in the inverse voltage, because you can see there is some other conditions here. Every time you can say here there is a change, here is a, so everywhere this rate of change is a dV by dt is very high, especially whenever there is a change in the conduction sequence. So, even though other valve is going to conduct this period, here you can say there is a U period here, sudden rise here, sudden change, and that may also cause the conduction in this period. Now, to avoid this, the factor 1 and 2, these factors means high peak inverse voltage and high jump here can be reduced by having the low voltage. Means if your voltage is reduced, what will happen? The voltage across valves will be also reduced, but that is not a better option, because if you are reducing the voltage, then for same power current should increase, and then it is not desirable. So, that is why whereas having low current can reduce the factor 3 to 4, because here 3 and 4 here you can see this will be again the change. So, and this will also reduce the power handling capability, and then that will increase the converter cost. The factor 2 and 3 can be improved by using small alpha, beta, gamma and the delta, but again the control operation is momentarily, sometimes we can do, but not always. The factor 6 here, that is here, the factor 6 here, that is the rate of rise of inverse voltage, that can be minimized by using your RC damper circuits in parallel to the each valve. However, the factor 3 can be improved with the high U. As I said, if you are having more U, that rate of rise will be reduced, and that can be done here. But if you are reducing U again, increasing U means your voltage will be reduced. So, that is another problem. So, this small function of valve results into the line to line short circuit, and sometimes it is a 3-phase short circuit, and it introduces lot of harmonics into the system. No doubt why it is happening, because it was in the blocking mode and then it is conducting. So, what happens? It may give the short circuit, because let us suppose your 6 and 1 is conducting, and suddenly 3 is conducting. So, 3 and 6 in same limb. So, there is a DC short circuit, line to line fault. So, whenever there is this type of fault, there are possibility that you are going to land up with the line to line short circuit in this AC side, and also the DC voltage will be 0, and it will generate the harmonic. So, whenever you are going to have malfunction of either rectifier side or inverter side, no doubt they will introduce harmonics into the system other than the conventional, because your voltage is not symmetric and you are getting some harmonics generated. Also, due to this, possibility will be there will be some dead short circuit, and we will see for other as well. So, for this case I am not going to analyze much more, because we can see for taking any case, and then we can draw the output voltage, and we can see how it is a line to line fault or sometimes 3 circuit fault is happening. Since it was happening only in the old HVDC stations, not in the modern, so I am not going to discuss much more about this. So, let us take second mall operation. This is also known as the fire through, sometimes also known as a short through. It occurs during the blocking period of valve, that is when voltage across this is positive. We saw the voltage positive in the rectifier operation is very small duration. So, the chance of this arc through is minimum in rectifier operation, but it is very common in the inverter operation, because the period of this positive voltage across valve is very high in the inverter operation, and that is why it is very common in the inverter operation, and its impact is almost similar to the commutation failure. Now, we will see that when we will talk about the commutation failure here like this, the impact will be the similar, but the case is not similar. Here you can say it was taking the current, but it is not so, and it is coming back. Here we will see how it is going to happen. I will just give you. So, that is why here it is written it is similar to the commutation failure, and this malfunction is due to mainly the failure of negative grid pulse. What we do normally, if the voltage is very positive across the valve, we normally give the negative gate pulse, always we maintain across the valve, so that it should not conduct. Why? Because you know there is a lot of jumps and dents, the voltage changes across the valve, again you can see the valve voltage. So, due to this there is a possibility that it can conduct, because the voltage is positive, any spurious signal is available, it will conduct. So, normally what we do here, we provide the negative gate pulse when valves are not in the conducting phase. Another is early occurrence of the positive grid pulse. Let us suppose you are giving every 60 cycle, but due to some reason your pulse generator circuit is giving pulse earlier to this, it will conduct because the voltage is positive. Because we want always the sequence, means after every 60 degree we want the pulses should be given to in sequence orders 1, 2, 3, 4 up to 6 and again 1. So, there is a possibility that your this function generator, that is a pulse generator circuit, is giving earlier to this due to the control action again, because your controller will be changing. So, if due to some problem it is giving this, then this operation may happen. Another is here the sufficient high positive transient over voltage on the grid or the anode. Here there is a, suppose there is a voltage rise, suppose high transient is occurring, then this may also happen, that is arc through can happen. So, the main problem with this arc through here, that it reduces the delay angle. We will see how is the delay angle is reduced. It introduces the DC component in the transformer side, means the AC side, because so many DC component will be generated and it will be going there, and it also changes the harmonic components, because earlier it was getting, we were getting this characteristic harmonics, but due to this we are getting some other harmonics in the AC side as well as the DC side. So, these are the three problem in this. Sometimes here the short circuit occurs once a cycle until arc through is removed or bridge is bypassed. We will see here. See in this diagram, here you can see at this point 5 and 1, here you can see this 1 is fired, here the 5 and 6 were conducting up to this period. Now, 1 was given a pulse here, then 5, 6 and 1 is conducting, are conducting basically here. Why? You can see the current here 5 and 6 here, this is 6, this is 5, means your valve 5 and 6 were conducting, right, because the current I 5 is positive and now I 6 is minus, it determines negative current here. This ID is there. So, then we give the pulse here to 1 and then during this period it is your U period where 5, 6 and 1 are conducting. Now, then commutation is over. Now, here we are having 6 and 1 are conducting. Now, at this point, let us suppose 3, we will see the voltage across 3 will be positive, and let us suppose there is a arc, this fault has occurred here at 3 at this point. Now, you can see the DC voltage becomes 0, because 6 and 3 in the same limbs are conducting. Means to see this again, you remember this diagram. So, let us draw it here. This is 1, 4, this is your 6, 3, here it is a 5, here it is your 2, and this is your converter. This is phase A, phase B, and phase C. Means at this portion what happens, your 6 and 1 are conducting, and here this arc through has occurred at this point. Now, what happens, as I said here the 6 and 1 were conducting. This is the case I am talking about inverter case. Why? You can see the DC output voltage is negative. As I said, it is a very much common in the inverter, because it is a longer period, it is your positive voltage is occurring across the wall. So, it was positive here, and due to this arc through here, this let us suppose it is conducting, and then there is a 6 and 3 in the same limb, it is here conducting. So, the output voltage here V D becomes 0. Now, what happens, your 6 and 1 were conducting, now 3 is also conducting. No doubt the DC voltage is going to be 0, but the voltage across this is rising, is increasing. So, there is a commutation between 1 and 3 will be successful, and then the current which was ID which was flowing here now going to be here. So, you can see there is a commutation between 1 and 3 is successful for the very shorter duration, because the voltage across this is rising very fast, the 3, and here it is 1 is decreasing. So, there is a successful commutation here 1 and 3. So, after that at point here you can see this D point onwards, your 6 and 1 here is conducting, 6 and 3 means here I can write in this graph itself. You can see here at this point here 3 is there. So, it is a 1, a 6, 1 and 3 are conducting, then commutation is over, means during this period here your 6 and 3 are conducting. Now, what happens at this point, now this is a turn of 4, no, it is turn of 2, yeah, it is a turn of 2. Now, the 2 is getting the gate pulse as in the sequence order. So, here it was 1, now it is we are giving the 2, and the 2 will be conducting, and the current from here to here will be the commutation will take place. Then now, what happens, your 2 and 3 are conducting, commutation here is a successful. Now, the DC short circuit which was 0 now is over, and the voltage will be, you can see here it is going to appear at this point, you can see. Once commutation is over, because here all are here conducting, means your 2, 3 and 6 are during this period is conducting, that is why DC voltage is 0, and then once commutation is there, you can say DC voltage will follow this. Now, this voltage here is coming, you can say the positive voltage is appearing across this wall during that instantaneous, but average will be negative, because mostly it is negative here. So, I can say at this point here the commutation, you can say this U period, when the commutation between 6 here and the valve 2 is successful, and here once commutation of 6 is over, now at this period your valve 2 and 3 are conducting. Now, valve 2 and 3 are conducting, it will conduct. Now, this is the turn at the certain point here that 3 is to be fired, and 3 is already conducting. So, it will continue it, because 2 was fired here, now is your 3 is getting pulse, it is conducting and it will continue, that is why you can say this is a voltage is coming up to here. Now, at this point, now we are giving pulse to the 4. It will be successful again, because 2 and 4 here they will be successful as usual practice we are assuming. So, between this period here your 3, 2, 3 and 4 are conducting, then and this time here we are having 3 and 4 during this period up to here. Now, here we are giving the pulse 5. At this point k, we are giving the pulse to the 5 because we are having in order 1, 2, 3, 4, then it is your 5. Now, we are just giving the pulse here 5 and the commutation will be successful, and now during this period your 4 and 5 are conducting. So, here during this period here you can see during this period your valve 4 and 5 are conducting, but at this point when this 4 and 5 are conducting, the voltage across 3 again becoming positive. We can check it here. Once your 4 and 5 are conducting here, 4 and 5 are conducting, the voltage across this you will find it is your EC, here it is your EBC will be positive, because it can be also understood most of the time the voltage across this is a positive. So, once it is a positive here EBC here, what happens if there is some problem in this valve itself? Means again there is a possibility it will be going for arc back or through. This fault can be again repeated, and then what happens, you can say there is again the commutation between 5 and 3 may take place. Means there was some problem here, it is not cured. Means if this is always in the positive cycle, let us suppose it is a conducting due to the some spurious signal or due to the some problem here in the manufacturing of this thyristor itself, then there is a possibility again it will conduct. If it is not conducting, then whole process is cleared. You can see continuously it is again here 4 5, then 5 6, then your 6 1 1 2 and so on, it will be continuously and it is a cleared. But the possibility once it is has occurred here, there is a possibility the same phenomena may occur here, because here again the voltage across this is going to be positive. You want to say something? No. So, you can see again the commutation between 5 and 3 is taking place, and then it is here the 3 is taking place here, and now it is your 4, and now here it is a turn of your 6 valve, because it is unless until you are blocking this 6 or you can bypass the bridge, means to do something, otherwise what will happen, you are giving a gate pulse here 6 because it is in the continuous sequence, and then again there is a dead short circuit because in 3 and 6. Now, after that here at this R point you are going to give the gate pulse to 1, but it will not conduct because the voltage across this it will be negative. Here we are giving, you can see at this, now after here this is your 6, here we are giving 1 pulse again here gate pulse 1, but at this point if you will check in the draw the voltage across this, because your this is the conducting your, this is the case where the 3 and 6 are conducting, across this voltage will be not positive, even though you are giving the gate pulse, your 3 will continuous. So, what happens, your 3 and 6 are, you know, see it is a conducting. Then here again we are going to have your 2 is coming, and then it will conduct, and there is a 6 and 2 will be successful, again we are getting the voltage like this. So, here in this case you can say the short circuit occurs once per cycle, no doubt here the short circuit occurs until arc through is removed. If you are not removing, then it will be continuously going. So, I mean to say here the short circuit occurs once per cycle. If it is removed here, means there is no, here this is arc through, means again that is not repetitive in the 3 valve, then it is removed and we are having the proper conduction, it is self clearing. But if still it is there, then we are having this the again more short circuit here for longer period, and that is very dangerous for the valves, because that may damage your the valve, etc. So, this is basically arc through concept in your mal operation of the converter. Is clear? Now, let us go for the misfire. In the misfire, as its name, it is a failure of a valve to ignite during a scheduled conduction. Earlier the two were this random in the nature depending on the fault condition, faulty of valves etc. Here you are giving gate pulse in the regular, just your pattern is 1, 6, 1, 2, 3, 4, 5, again 6. So, in regular sequence you are giving the pulses to these valves, you get the gate pulse, but it is misfired, it is not conducting. The region may be various, because the voltage across this is a positive, it should conduct, but due to some problem it is not conducting, and that is known as misfire. So, this can occur either in rectifier, it can occur in inverter, but it is a more severe in the inverter, because this is again just like a simple, it is just like your commutation failure. Because what happens, suppose your 6 and 1 are conducting, then you give the pulse to 2, it did not conduct, then what happens? Then it will continue, then the number of third will come, and then the commutation between 6 and 3 will be there, but dead short circuit is there. So, it may be either due to the negative gate pulse or positive anode to cathode voltage or fault in the valve. So, it is due to the certain problem, it is misfired. The effect of misfire in the inverter is similar to the commutation failure and is also similar to the arc through. I said arc through is also just like a commutation failure. The consequence is same, effect is same, but the phenomena is different. Now, so let us say condition that your valve 6 and 1 are conducting and valve 2 fails to ignite. So, what happens, valve 6 and 1 will continue to conduct, and thereafter valve 3 will conduct, and there is a discharge circuit during that period, that is a smaller duration. There is a small jump in the voltage at the beginning of the short circuit and the large jump at the end of the short circuit. To verify this, let us see and draw the voltage. This is as our usual diagrams, line to line voltage, and here if I can say our EBA is your commutation voltage of valve 3, and now I am talking for the rectifier end. Similarly, we can talk about the inverter end misfire condition. Here I am just discussing the rectifier because it is very simple. Inverter you have to delay again, and then you have to measure from this side rather than this side alpha. Let us take a ideal condition, means u is 0. One condition we can have a u also, we can have u 0 also, and there will be no difference in the generality. So, I can take, let us suppose your alpha here, alpha is your 15 degree, and now your 6 1 are conducting, means what will be your output voltage. You know your firing pulse here, this is a 30 degree, this is a 15. So, here your 3 will come, here your 4 will come, this is I am just writing the firing sequence. Here your valve 5 will come, here your 6 will come, here your 1 will come, and then here your 2 will come, right. And then again we are repeating here 3 at this side, and then continuously we are monitoring. So, it is very easy to, I missed something, 4, yeah, here 4, and so on and so forth. So, now we have to write the line voltage as usual practice. So, it is EBA, here it is your ECB, good, here it is EAC, here it is your EBA, and now this voltage will be your ECA, this voltage is EBC, this which is left out, this voltage is EAB, this voltage is EBC. Okay. Now, you can see when 6 and 1 are conducting, what will be the output voltage. We are giving the pulse here in the rectifier mode. You will just see here, this is a 6 and 1 are conducting, it is A, and here it is a B. EAB is the output voltage, and EAB output voltage here it will be this much. So, here it is starting at this moment. No, this is your just 1 is given. So, here the 6 1 is conducting E here. Now, we are coming here. Now, it is given your 2, but it misfires. Means it is misfire, means your EAB will continue. So, it is here misfire. I can write here. So, what happened? It will be continually conducting till here. Okay. Now, we are giving the pulse 3. What will happen? There is a short circuit, and finally, here there is a voltage will be 0. So, you can see now in the conduction pattern here during this period 6 and 1 are conducting till here. The commutation between 3 and 6 will be over, 1 and 3 will be over, and your 3 and 6 will be continuing here 3 and 6 during this period. You can say the output voltage here. Now, when the 4 is coming, now we have to see what will be the voltage. Now, there is a commutation between 4 and 6 will be happening. So, your output voltage will be EBA means certainly it is going here, and it will be continuing conducting here, and then we will find the sequence continuously. So, we can come back here to make it our clear here. It was here, I can just make here the complete cycle from this side. It is coming here, then it is going to be EBA here, and now it is coming here, and then here again, this is here, and finally, we are giving here. So, you can see the DC, this is a DC output voltage in case of misfire when it is operating in the rectifierment, because alpha is less than 90 degree, and you can say most of the time the voltage is positive. In this, you can see the problem is here huge surge the voltage at the end of conduction, huge voltage is jumping, and this may lead to the puncture of the valve, some of the valves, and that is sometimes not desirable. So, here it is a rectifier. Similarly, you can draw the valve voltage of any of the valve on the same plane, and you will find it will be just down the voltage here. So, you can draw the valve voltage as well, and your valve voltage, I want to draw here for again valve 2. Let us suppose I want to draw the valve voltage 2 and the same axis. So, what happens? We can start here. From where we can start? Let us suppose your 3 is fired here. At this case 3 is fired here. Now, what will be the voltage when your we can start from 4th, I think better. 3 and 4 are conducting. Yeah. So, then it will be one cycle basically. It is better to go for the complete where the anomaly. So, 3 and 4 are conducting. So, the valve voltage 2 I am drawing. So, 4 here it is your EA, and here is EC. So, EAC will be the voltage. So, during this period here EAC, where is EAC? EAC is this was here, and when the voltage is there, is EAC here. You see this is EAC, this is EAC is there here. Okay. Now, once 5th is coming, it will not change. So, it will be continuing here up to 6, because this conduction will not change the voltage across this, because the voltage here this will be always EC, and the voltage whatever they are conducting, the voltage will be appearing here. So, whenever there is a conduction change from here, then the voltage will change, otherwise it will continue, simple rule. So, now it will be same. Now, once it is a 6 is there, now it is EBC, and EBC is your EBC is here, you can say very well here, and it will be continuing to here. Now, then it is 1, and it will continue to conduct, because here it will be your this voltage, this period 1 is there. So, it will not change the voltage. So, this is going to be this, and now here once 2 we get the voltage, but it is not conducting. So, what happened? The voltage will be again, because here it is conducting. Now, from here onwards what will be the voltage? The question is this. So, it will continue, and finally, we have to reach up to this point. Once this voltage is, this is a dead short circuit, this EB will be coming and it will follow the EBC here, and it is EBC is there till here at this point, because then again fourth is coming here, and then we are getting this, where is that? This is, we are here, and then at the 4 we have come back here. This is your, we were following EBC, EBC was this was here up to this point, and then it will be coming here suddenly here, and this is the valve voltage. So, basically this is the voltage, you can say not as that smooth due to this here the different voltage appearing, otherwise there was some change here, and it was basically the conduction pattern here, but it is not conducting. So, in whole cycle the valve 2 is not conducting, so the voltage will be not 0, but you can say most of the time here again the voltage is positive even, because once it was conducting here too, it will be 0 here. So, this is valve 2. Similarly, if you will go for your inverter operation, you will find that this is totally, means again the reverse end, the voltage will be going, the DC voltage will be the downside and the valve voltage will be the other side, and we will see that due to this is just like a commutation failure, because if it is coming in your inverter side here, you are operating, there is a possibility that once 2 is misfired, here 3 you are giving the gate pulse 4, it may not conduct, because you have to see the voltage across this should be positive at that time, because this is the condition. So, this severity will be the different than your rectifier. Rectifier it will be, because you can say here this is positive, it will be the conducting. So, the inverter operation is basically the typical operation always, and we have to be very sure that the voltage, once we are giving the pulse and the voltage across that valve is positive, then only it will conduct. So, for each instant you have to check what is the voltage across that valve in the sequence order. So, this is your basically misfire. So, in this lecture, in this first lecture, we just say arc back and the fire through and the misfire, the 3 mall operations we saw. Next turn will, and next lecture 2 we will see the commutation failure, how this is happening, the single commutation, and then we will also go for the 2 commutation in the same cycle, then we will discuss about the protection as well. So, with this I can close this, and in the next lecture we will see the commutation failure of the inverter side. Thank you.